Okay, so good afternoon. So today we'll continue our discussions on memory management, and hopefully I get to start talking about caching. So we'll see where this takes us. Okay, so just a kind of a review of what we were talking about last time. So we talked about the idea of paging. We divided the virtual pages and the virtual address space and physical address space into these smaller chunks of pages. And then in the page table, we do the mapping between virtual page number to physical page number. Now, we observed that usually in virtual address space, there are many pages that are not used, right? So let's say you have a hello world process. So your hello world process has some number of kilobytes of code, probably not much data. Maybe the string of hello world is stored somewhere. You're probably not going to use heap and a little bit of a stack, maybe if you have a function. So, excuse me, your virtual address space is very, very small. Like the virtual pages that you're using are going to be only a few pages that you're going to be using. However, you have gazillion number of virtual pages, right? So a lot of them are not being used. Only few of them are being used. With page table, however, you have to have a single entry per virtual page, even if you're not using them. So you're storing a page table entry for every single virtual page in your address space, even if you're not using it. So in this example that you can see, so these are the virtual page, these are the page table entries corresponding to the virtual pages that I'm not using. So I have a lot of these empty empty spaces in my virtual page table. So the size of the page table, as we discussed, the size of the page table is basically the number of virtual pages in my address space, not the number of virtual pages that I'm using. Okay, now, and as we discussed, this is going to be really huge. For a 64-bit system, I need 32 petabyte of storage or memory to just store my page table. Yeah, so this is a lot bigger than 32 gigabyte physical page that is available today, for example. Okay, so the idea here is, so now we want to address that issue. We want to make the size of our page table small, and hopefully we want to get, so the goal is use as many page table entries as virtual pages that your program uses. The number of, so use as many page tables as the number of virtual pages that your program uses. So reduce the number of page table entries that you need in your page table. So that's the goal. Now let's see how we can achieve that. We're going to do a two-level here example, two-level page table address translation, and then we'll see how this is saving us on the page table. Okay, so let's say I haven't changed the offset bits, so let's say my pages are 4 kilobytes, so I need 12 bits for offset. Okay, so that hasn't changed. Now the rest of the virtual address space, the rest of the bits, the 20 bits, I'm going to divide it into two different sections. I'm going to pick the first 10 bits and call that virtual page number 1. And then the next 10 bits, I'm going to call it virtual page number 2, or virtual page index 1 and virtual page index 2. Okay, now how am I going to use that? So I'm going to make my page table pointer to point to the first level of page table. Then I will use the first 10 bits to index into this page table. Now, how many entries do I need? How many entries here? Well, because I'm using 10 bits, this means that I have 2 to 10 entries. So 2 to 10 entries. Remember, if I were to use all these bits for page table, I would need 2 to 20 page table entries. Because I have 20 bits, so I would need 2 to 20 page table entries. Now, at this point, I have 2 to 10 page table entries. Orders of magnitude less, right? Okay, so then what? Now, after I index, I'm going to use whatever is in this page table entry to point to another table. So every one of these page table entries in level 1 is going to point to another page table at level 2. So the rest of them are also going to point to page tables. Now, here comes the how we're going to use this second level page table. We're going to use the rest of the address space, the virtual page 2, to index into these new page tables. Now, how many page table entries each one of these guys have? So this is also 2 to 10 page table entries, right? Because I have 10 bits. Now, here is what you should be asking at this point. You should be asking, okay, how am I saving a space here? The answer is, for anything here, for any page table entry here that is null, how many page table entries am I saving? So this is basically saving 2 to 10 page table entries because it's pointing to nothing. So I'm saving 2 to 10 page table entries. The next one, the same thing. For all the ones that are null here, I'm saving 2 to 10 page table entries. So I'm saving a lot. In the previous model, I needed to have a single page table entry for every single virtual page. Now, if there is a range of virtual pages that I'm not using, their corresponding first level could be just null, and then it's not going to point to another page table because the other page table, the size of that is going to be 2 to 10 page table entries. So I'm going to save that. I'm not going to use that. That's the memory that I'm not going to be using. So in our case, let's say in our hello world situation, right, I'm probably only have 3, maybe page table level 2. So at the end, the number of page table entries that I'm using is a lot less. So it's kind of like 2. Let's say if I'm using only 4 page tables, so the first one is page table number 1, and then let's say 3 page table number 2s. That's in total 4 page tables. So I'm going to be 4 times 2 to 10 page table entries. So that's basically 2 to 12 page table entries. Now compare this to the original page table design that needed 2 to 20 page table entries. So this is orders of magnitude less. And that's how we're saving memory for our page table. Okay, let me clean this up so that we have space for the rest of the slide. So here at the second level, I get my physical page number, and then I append my offset, and this gives me an address to my physical page, and I can go and read the byte that I wanted in this page. So this is two-level page table. The same. Every page table entry in level 2 is going to be pointing to a physical page in memory, right? Okay. Here is an example. So this is the same example as we saw initially with this with today's lecture. Now, as you can see, I have reduced the number of. So initially in the previous one, I had 32. Initially, I had 32 page table entries. Now with this design, my page level number 1 has 8 entries, and I'm only using 4 of them. So 4 are not pointing to anything, so I don't need to store anything for those. And then the 4 that are pointing, each one of them is pointing to a page table level 2 with 4 entries. So in total, I have 4 times 4 page table entries, plus the initial 8. So this is 16 plus 8, that's 24 compared to 32. Although here the saving is not that obvious, that how much I'm saving, but if you scale this up, you'll be saving a lot, right? In actuality, the comparison is going to be meaningful. Okay, so why did the original design needed 2 to 20 page table entries, and this is only 2 to 10? Right. So initial design, if I go back, so if you look at the original design, so original design is this one. You get your offset, let's say to the 12 bits. Now the rest of the bits are going to be your virtual page number. So let's say if this is 32 bits, that would be 20 bits, right? So for your page table has to have 2 to 20 entries, right? Because you have 2 to 20 virtual pages. So your page table entry has to have one. Your page table has to have 1 entry per virtual page, and you have 2 to 20 of them. So that's where the 2 to 20 comes in the original design. Now in this one, for the entries in page table level 1 that you're not using, you're saving 2 to 10 because each one of them is not pointing to another table. So what is the size of each one of these tables? It's 2 to 10 page table entries. So each one of them has 2 to 10, right? So if something is here null, it means that you're not saving 2 to 10 page table entries. Now, the first level 1 has 2 to 10 page table entries. Each one of these guys also has 2 to 10. Now, in total, in this particular example that you can see, I have 4 page table. Each one of them has 2 to 10 page table entries. So I'm getting 2 to 12 page table entries. Again, in this particular example, right? Different examples could be different. Now, if you have an application that uses its entire virtual address space, so if let's say I have an application that none of these are null, if all of these entries in level 1 are used, so if all of these guys are used, so each one of them is going to point to another table. So in that case, well, you actually have added overhead because you now have this level 1 as an overhead because you are using 1 page table entry for every virtual page. And you have also added this level 1 page table, which is extra. So you added a little bit more, but still, so that's the, you know, the extreme case where you have an application that uses its entire virtual pages, virtual memory, which almost never happens, right? But normal application, normal processes, they have these holes in their virtual space, virtual address space. And for those holes here, when page level number 1 is null, then you're not storing page table level 2 for that. So that's where you get the saving. Okay, so the way you're translating, right? If let's say my page table level 1, so in this particular example, each page is 8 bytes. So I put aside 3 bits for offset. I'm assuming that I'm using, for the rest of the bits, I'm using 3 bits for page table level 1 and 2 bits for page table level 2. So my page table level 1 has 8 entries, and so this is 8, and every one of page table level 2 is going to have 4 entries. Now I look at my address. So look at the first one that indexes into the first level. This is going to give me a pointer to the second level. Then I use the second 2 bits to find my translation here, and that's where I get the physical address. So I get the physical page number. I append my offset, and I get my my answer, which, by the way, seems to have an error. So this should be 0. There's something funny going on here. Yeah, so this should be the number here is basically messed up, right? Oh, I see. So sorry. So this my apologies. So I think this address corresponds to this one. So anyhow, so I thought that this address is pointing to this green box. So never mind. Everything is okay. So anyhow, the address you get is basically 1000000. So that's the address that you're going to get for this memory. Okay, now you can use the same idea with segmentation. So if you remember, we started with segmentation. Now we can merge segmentation and paging. So we can have different segments, and then for each segment we can use different number of pages. So again, this is the number of bits that I'm going to put aside for my page size. Let's say 12 bits or whatever. Then if I have, let's say, 4 segments, then I need to put aside 2 bits for segment number. So different number of segments, different number of bits required. And the rest of it is going to be my virtual page number. So initially, I use my segment number to index into segment map. And segment map gives me a pointer to page table. Then I use my virtual page number to index into my page table. And once I do the translation, then I just append my offset to get my end result. Now, there is a chance to add permission here in page table or add permission here. You could also have permission in segments so that you can assign a segment permission. You can make the entire segment, for example, read only. For your code segment, you can make it read and execute. For your shared library, you can just make it again, read and execute. But anyhow, so you can assign permission granularity of segments, or you can assign permission and granularity of pages. So I'm going to just be a little bit faster. In x86, in x86, you have this global descriptor table. So this is basically the same thing as segment table. And this global descriptor table will have pointer to first level page table. Now, when you context switch, you can just save this pointer in your TCB or PCB, and then change this pointer to point to the segment table for someone else, or the new thread that you're going to run. Now, in x86, we use multi-level page table, so it's not just a segment and a virtual page. It's going to be a segment and then 4 levels of paging for 64-bit, and then 2 levels of paging for 32-bit. So here is the picture for 32-bit system in x86. The page size is assumed to be 4 kilobyte. So for 4 kilobyte, you need 12 bits of offset. Now, in a 32-bit system, you have the remaining is 20 bits. It's divided into 2 10-bits. So this is VP level 2, and this is VP level 1. Now, you might ask, where is the segment number? So if you remember, I showed you a segment number and then virtual page number and then offset. Now you don't see a segment number here. So where is this guy? In x86, the architects have cheated. So the segment number is put into registers. So you have a stack segment, you have data segment, you have code segment. For example, CS code segment is a register. So you can put the segment number in that register, right? So it's kind of like cheating. It's kind of like expanding the 32-bit of virtual address and appending the register to it. So depending on the address, it recognizes the segment, and then it uses the associated segment number to find the page table for that segment. And then once you have the page table, then you can just go through the levels of indirection. Okay. Now in a 64-bit, you have from 0 to 63. With the same page size, you need 12 bits for offset. Again, now the rest of them are going to be divided into 4 levels of 9 bits per level. So each page table, intermediate page table, has 2 to 9 page table entries. These bits here at the end from 48 to 63 are not used. So in essence, the maximum virtual address range is from 0 to 2 to 48. It's not 2 to 64, right? The reason is even this is plenty, right? You don't need to go all the way to 63. So they just cut it, and they're not using these bits for address. in 64-bit system. Now, one thing I have to note is that the size of each page table entry in a 64-bit system is 64 bits. So compare that to this one. This one, each entry was 32 bits. Now this in a 64, each entry is a 64-bit page table entry. We'll look at what comes into a page table entry in a bit, but each one of them has 64 bits. Okay, now let's see how much coverage you get per page table. So your page is 4 kilobyte. Now here, a single page table, level 4, the last one, has 2 to 9 page table entries, and each page table entry is going to point to a physical page. So each one of them has coverage of 4 kilobyte. So this becomes 1 megabyte. Is that 1 megabyte or 2 megabyte? That's 2 to 12 plus 9 is 2 to 21. So that's 2 megabyte. So with last level page table, you're covering 4 megabyte of physical memory. Now, if you go one level higher, you have again 2 to 9 page table entries. Each page table entry is going to point to a page table level 4, and each page table level 4 is going to cover 2 megabyte. So I can just multiply this by 2 megabyte. And this is 1 gigabyte. So a single page table level 3 covers 1 gigabyte of physical memory. And you can just go up, right? You can go up the ladder. Each page table level 2 covers 2 to 9 times 1 gigabyte of physical memory. I got a question. Why is each page table 64 bits if each page table only has 2 to 9 page table entry? Okay, what is the purpose of page table entry? What does it do? What's the main purpose of it? Main purpose of it is to have an address of physical page. Right? So the reason it's larger in a 64-bit system is because usually in modern 64-bit systems, you have larger physical memory, right? So our physical memories are usually large. They're, you have more than usually 1 gigabyte or 2 gigabyte of RAM. You have 8 gigabyte of RAM. You have 64 gigabyte of RAM. Now, if you have, let's say you have 32 gigabyte of RAM, if each page is 4 kilobyte, then how many pages do you have? So the number of pages is going to be 2 to 5 times 2 to 10 times 2 to 10 times 2 to 10, right? Bytes, that's how many bytes you have. So this is kilobyte, megabyte, gigabyte, and then 32 gigabyte. And then each page is 4 times 2 to 10 bytes. So I can just cancel this. And then I can cancel this with this and get 8. So I have 8 times 2 to 10 times 2 to 10 different physical pages. So that's 2 to 23 different physical pages, right? So for 2 to 23 physical pages, I need at least 23 bits. So I need at least 23 bits for physical page number, right? So my page table entry should at least provide 23 bits. Now there are much more. So you know, if you're provisioning your system, you can assume that the memory is not going to be only 32 gigabyte, right? Your memories might be actually bigger. You might provision for a system with 128 gigabyte. So for that, you need more number of bits for your physical page number, right? So the reason this is bigger is because we need more number of bits for our physical page number. We also, as we will see, we have also added some number of accessory bits to help operating system, as we will see. So that's why each page table is bigger. Now, in a 32-bit system, the maximum physical memory you can support is, if I'm not mistaken, is 4 gigabyte. So that's the maximum memory you can support with 32 bits. So the number of bits that you need for your physical page number is going to be a lot more limited. So that's why your page table entry can be smaller in a 32-bit system rather than in a 64-bit system. Okay. Here comes a x86 64-bit page table entry. 27 bits are reserved for page table number. So this actually tells you what is the maximum, if you were to use this system, what is the maximum physical size of your system. Although one thing that is important is that the size of page, the size of your pages is important, but this supports 2 to 27 physical pages maximum. Now you can multiply this by the size of each physical page to get the maximum size of physical memory that this could support, right? You can, the software could potentially change, for example, actually it's not that much software choice, but then x86 provides some leeway to set the page size, because the hardware also needs to know what the page size is when it does the page table walk. But I'm not going to get into it. So the bits that are interesting to us, and we'll see them being used, is the first one is here, the V bit. This is valid invalid. The next bit that is usable is the W. So does this page have a write permission, or is it just a read permission? The other one is this D1, and also this A1. Has this page table been accessed? So if hardware accesses a page table entry, it sets the bit to 1, indicating that this translation was used, meaning that the application needed this translation, meaning that the application needed to access this page. If the application writes to a page, then the hardware can set the dirty bit to 1, indicating to the operating system that the content of this page was updated. The copy on write, here we saw this bit being used, for example, when we talked about fork. So it has its own bit here. The other one that is interesting is this last one, no execute. So in the 32-bit design, Intel didn't provision any bit for execute access. So there was no execute bit with page table entries. And that was very annoying for operating system designers. They have to come up with software ways to deal with it. when AMD took over designing the 64-bit page table, they added the execute bit, but interestingly, they added at the end. In my opinion, this is kind of rubbing it to Intel's face. It got its own bit at the end for execute. Anyhow, now if you want to share, you can share at different levels, right? You can share the entire, for example, entire page level 1. You can share that level. Let's say if you want to share 1 GB, for example, you can share a page table level 2. If you remember, page table level 1 was covering 2 MB. Page table level 3 was covering 1 GB. So if you want to share 1 GB between processes, you can just share it at level 2, right? Level 3. Both of page table entries level 3 could point to the same, both page table level 2s could point to the same page table level 3. And that way you can share. So sharing is possible at different levels, basically. You can share at the level of a page, a single page could be shared, or page tables could be shared between processes. So in this example, I'm sharing a page table between 2 processes. So segment 3 of process B and segment 1 of process A are both mapped to the same page table. So both of them share the same page table. Therefore, they're sharing all the pages in this page table, right? So the granularity of sharing is at segment level in this example. Okay, so here is a slide. This is a slide. If you understand this slide, this means that you understand address translation, although it's a side, but it's actually very deep, the conversation in this slide. So let me walk you through this example. But before I do so, I want to remind you an example we saw before. So let's go back to this example here. If you remember this example from the previous lecture, I had these virtual addresses for each line of code, right? So each line of code had its own virtual address, and PC program counter had this virtual address, right? And then if I wanted to jump, for example, to let's say if I wanted to jump to strlen, I would set PC to this virtual address for this strlen. So these are called absolute addresses or virtual address. Am I spelling absolute correctly? So sorry if my dictation is wrong, but these are absolute virtual addresses because they're like, I have a virtual address. An alternative is, instead of this jump to strlen, maybe I can say jump 3 bytes from wherever you are. So I can just get the PC and add or negate a number. So this becomes a relative address. So relative address says wherever you are, go 10 bytes forward or 2 bytes backwards or 20 bytes backwards or 40 bytes forward. So it doesn't care what the absolute address is. It cares about where you are now and where that address that you want to jump to compare and relative to where you are right now. So it says 10 bytes forward or 20 bytes backwards, something like that. So I'm not using actual absolute addresses, I'm saying wherever you are, add 10 or subtract 20 or whatever. So relative to where you are. Okay, so with that introduction, let's go and talk about this slide. So when you're compiling and loading your shared library, so this is a library, this is a code that is going to be used by multiple processes. So multiple processes are going to use this code. Now, if you have any static variable in your code, like any variable that is defined and used in this code, each process needs to have its own copy of these variables. You cannot share the data in a library, because if you share data, then you're messing things up. Now, this means that each process is going to have its own data, and they're going to get permission to read and write to that data, right? Because each one of them is going to have different variables. I mean, the same variables, but different values for those variables. So each one of them is going to have its own copy. Now, when it comes to the code, however, the code is going to be used. That's where the shared comes. Multiple processes are going to share the same code. Now, if you remember, and this code is going to be read and execute, right? We don't want to allow them to write, to change the code. So it's going to be read and execute. Now, the code has to be position independent, meaning that I should not use any absolute virtual address in my code. So if I have a jump, if I have a a for loop, or if I have a jump to another function, I cannot jump to an absolute virtual address. The reason is each process is going to have its own virtual address range for this shared library. So process A, so if I have process A and I have process B, so both of them have their own virtual address space. Now, it might be that I'm mapping this range from process A and this range from process B to this shared library. So these are physical addresses, and these are virtual addresses. VA for process B, VA for process A. Now, different virtual address ranges are used and mapped to the same physical address range, so that process A and process B are sharing the same library. Now, if in the code, in my shared library, I have something like jump to some absolute address, x0, f, c, blah, blah, blah. Now, this, in the context of process A, could be mapped to something, and in the context of process B, it could be mapped to something else. So executing this same code in the context of process A will jump to some address, in the context of process B jumps to another address. And this is absolutely not what I wanted. I wanted this jump to a certain code, no matter where it's executed, in process A, process B, process C, I didn't care. So if I use absolute virtual address, I'm going to be in trouble. Therefore, when you compile and load your library, usually you tell the compiler that I am compiling this code for shared library. So you set flags telling the compiler that this is a shared library. The same thing when you're loading your shared library, you tell the operating system that this is a shared library. because all the addresses in your shared library are going to be position independent. They're all going to be relative addresses. You cannot use absolute addresses. Now, the same works with data. I mentioned that each process gets its own data and they have read and write access. So now if I have something in my code that says, I don't know, load, I don't know, some data to some register. Now the address of this data, so let's say the address of this variable to this register. Now the variable could be mapped to different ranges in different processes. I cannot use an absolute address for my variable because I don't know where it's mapped in different processes. Now, when you compile this using and you tell the compiler that this is going to be for a shared library, the compiler produces for you a global offset table and puts this table at a certain position in your code. It's usually at index 0. Resides this global offset table. So then the compiler puts a relative address to this global offset table. It says, for example, look at row number 10, for example. This is fine, right? So it says go to this global table and look at row number 10. Now, this global table will have different values in it in different processes. So when you create that data for your shared library for this process, you go and fill this global table. Now, whenever this line of code is executed, it goes to that table, and at this point, this table has the address of this data. So you're fine. So your data reference will be with the level of indirection. So the level of indirection is to go first to this table, and then from this table, get the actual address for your data. The same actually happens for your function calls, for your procedure calls. Let's say, for example, your shared library uses another function from another library. You don't even have the relative address to go to that function, right? So instead, you index to this procedure linkage table. You say, go and look at row number, I don't know, 15 of this table. And then when at runtime, the mapping happens, operating system fills up this page, this procedure linkage table, and fills it with correct addresses. So you actually go again with the level of indirection. You first go to this table, and then you find the address to the procedure that you want. Okay, so that was a side. And now going back to multi-level address translation and having the final discussions. So allocation is good because and easy because we're using paging. So management of memory is easy. Again, remember, we can just use that bitmap to know which pages are allocated, which pages are not allocated. Oh, so that's the second point. So allocation is easy. The first point says that you basically you're using as many page table entries as virtual pages that are being used. So you don't need to store page table entries for virtual pages that you're not using, which is usually a lot of virtual pages we're not using. So the size of your page table is limited to the number of virtual pages that you're using. Sharing is easy. You can actually share at page level, at different page table levels, or at segment level. Now, the downsides of this is that basically you have to have more than one access to your page table to do the translation. So compare this to a flat page table. For every translation, we needed one access to page table, but it was just the size of page table was big. Now you will have to have extra accesses to your page table to get the translation. And also, depending on the size of your page, you could end up having internal fragmentation. I don't know if, I don't have the internal fragmentation, but internal fragmentation is another pitfall or another weakness of this, similar to the previous model with page table. Yeah, okay, so we went through all the important stuff. Now, the last translation method that we're going to look at is going to be the inverted page table. Now, so far, all the methods that we have seen are forward page tables. In forward page table, you basically, the size of your page table is proportional, sort of, to the number of virtual pages that you're using. So the more virtual pages you use, the bigger your page table becomes. So initially, your page table might be small, and then as time passes by and you use more virtual pages, then your page table expands and becomes bigger. There is no limit on how big your page table could become. Your page table could grow, and that might not be good. If you have a process that uses a lot of virtual pages, then we get to this territory that our page table could become so big, and we don't have enough space to just store our page table. Alternative is to fix the size of our page table. Say, I don't want my page table to grow from a certain size. So I want my page table to have a fixed size. Now, that's what inverted page table does for us. Now, in essence, inverted page table is nothing but a hash table. So the way it works is you get your virtual page number and you hash that to get your physical page number. So basically, physical page number is equal to the hash of virtual page number. So this basically means that your page table is of fixed size. It's how many entries your hash table has. That's all. That's how many entries you need for your page table, right? So that's basically what it is. Now, the difficulty of this is basically implementation of this hash table in memory. So potentially we want this to be done at hardware. So the hardware has to implement this hash table. So extra complexity for hardware. The other difficulty with this is poor cache locality. So if you know anything about hashes hash different keys to random values, right? That's where we get the power of hashing, because we want to avoid different keys to be mapped to the same value. That's why we randomly distribute them. This comes at a cost, because your application could use, for example, virtual page number 1, virtual page number 2, and virtual page number 3. So these are virtual addresses that are consecutive, right? But then when it goes to the hash, the hash of virtual page number 1 could be physical page number 100. The hash of virtual page 2 could be page number 1, physical page number 1, and the number 3 could be hashed to number 50, for example. So now you have a lot of missed opportunities for a spatial locality, right? Because you're distorting your accesses. The access jumps from here to here. You're going to jump from physical page number 100 to physical page number 1. So there is no spatial locality here. Whereas in previous designs, we could have, it was up to us how to map them. So the operating system could have actually mapped virtual page number 1 to physical page number 10, and then mapped virtual page number 2 to physical page number 11, and maybe virtual page number 3 to physical page number 12, right? This was possible in the previous one because it was up to us how to do the mapping. Now with this new design, when you're using the hash, well, the hash decides for you where they're mapped. So it's not up to you. The other thing is, what happens if two virtual pages are mapped to the same page, to the same physical page? It's inevitable because we have more virtual pages than physical pages. So in those cases, then the difficulty is to add extra hardware to take care of which one of these translations are valid, right? You have to know if the translation for this virtual page is valid or the other virtual page that is mapped to the same value. So you need extra complexity to take care of collision between different keys. So here is an example, right? If you have a case where you have, I guess in this example I have 4. So I don't exactly remember how many. I think I have 32 pages. So basically, my inverted hash table gets the virtual page number and spits out a physical page number. That's all it does. So basically, the size of my page table is not proportional to the size of virtual address space. It's limited to the size of the physical memory. And the size of physical memory is usually limited. Okay, so next topic is who has to do the address translation? Are we going to do the address translation in hardware, or are we going to do address translation in software? Now, do we need hardware for address translation? The answer is not really. We don't need hardware. We can do it in software. So, for every address, I can raise a page table fault and then go to kernel, and then kernel tells me where this virtual address is mapped internally. Kernel can have its own data structures to have the mapping. It doesn't need to use page tables. It can use any data structure it needs to do the translation. But it's very slow. So it's not necessary in terms of functionality. We can do it as software. The kernel can do it. But when it comes to performance, this is going to have a huge performance cost if you want to do it as software. So usually, and by usually I mean often or always, page tables are implemented in hardware. So the operating system sets the page table entries, so does the mapping, and tells the hardware where page tables are. And then the hardware does the page table walk. So the memory management unit, MMU, on every memory access can go through page table to do the translation. So it happens in hardware. So hardware provides that support. it gets a virtual memory. It does whatever it needs to do to translate it to a physical address. And if it cannot find the translation, then we can go to the operating system by a fault handler to see what we should do. So if hardware cannot find the translation, then it will ask for operating system's help. Now this is relatively fast. It's much better if we do that hardware. We don't need a mode transfer. We don't need to wait for kernel code to run. It's just a bunch of memory accesses that the hardware is going to do. Now this comes with the cost of inflexibility and complex hardware. So first of all, we have to have a complex hardware that understands page tables, that can do, go over multiple levels of page table. It can, interpret virtual address. So all the logic that we talked about has to be implemented in hardware, and that's a hard thing to do, believe me. So it's a complex hardware and it's inflexible. So basically, operating system doesn't have much flexibility. You have to follow whatever hardware tells you to do. So the operating system has to fill in whatever hardware needs for this translation to happen. And the alternative to do that software gives you the utmost flexibility. You can do whatever you want in software, whatever data structure you want, whatever algorithm you want to use to translate. It's just you're gonna, at every translation, you're gonna invoke a fault handler to do the translation, which is pretty slow. And as we'll see when we start talking about caches, we're gonna cache the translation to speed this process up. Okay, this is just a summary of everything that we talked about, so you can just look at it yourself, and we can move on to the next topic. Okay, so I'm glad I got to start caching today. Okay. So somebody is asking what type of questions can we expect from address translation in this exam? So, you have to know all the basics. So look at the quizzes. So let me do this. If you go to the questions, the archive, I'm gonna pick like just a random. I bet there's a address translation question here. So let's look at the midterm here. So basically, the true falses are going to be the same as your quizzes. So in your final exam, you will have true false questions, and I will try to just pick questions from the quizzes that you have seen. So although we had the random selection for questions, so not everybody saw all the questions, but I'll try to pick true false questions from the quizzes that we had. We then will have some multiple choice questions that would be also similar to the quizzes. It's just multiple choices, but similar style. Short answers. Let's see if this exam had a. This is if it had a memory translation. Probably the memory translation was in final. So let's pick a final. Again, true, false, short answer. Usually the way it works is that I'm going to give you a page table entry filled up, and I ask you to translate a bunch of addresses for me, depending on different methods. Like, I give you page size, I give you the number of levels of pages, and then I ask you to use the page table that is provided to do the translation. So that's one example. There are multiple different examples. So definitely take a look at these exams. So this one that I picked doesn't seem to have a page table question, but it's usually there. Yeah, this one didn't have. So just go through all these recent exams. You will see questions. Again, if you do the quiz this time, you will see some true/false questions with page table. And then if in the exam, I can ask you to do the translation for me, given all the information that I give you, or I can ask you to compare different methods and tell me if I need a certain thing, which one is better. Okay. That's that. Let's go to, really want to start caching today. Okay. So what is a cache? So cache is, I'm going to give an example. Let's say you're somebody's secretary and or your own secretary, and then you have a lot of documents in your in bunch of compartments stored in your room. Now, every time you need a certain document, you're going to go and search this entire all the compartments and all the boxes that you have to find the document that you need. And then once you're done with that document, you're going to go and put it back and then go for the next document that you need. Now, this is pretty frustrating. For each document, you go there and you come back. Now, it becomes more frustrating if you are going to go for a document that you very recently accessed. So if, let's say, you needed document A yesterday and you used it and put it back, and today you went for document B, and maybe tomorrow you're going to go back to document A, going back to those boxes and compartments to again find document A is frustrating and annoying. If you know that this document A is a document that you're going to need a lot during this week, maybe you're filing your taxes and there's this document that you really need in this week, maybe it's better to put it in a folder and put that folder on your desk, so that next time you need the document, you can just look at the folder and there we are, the document A that you needed is there. And then you use it, and then tomorrow or 2 days from now, you might need it again, so you go to that folder. Now, you can't overuse this. You can't bring all those documents in your compartments here on your table and put them in these folders, because then you have just moved your boxes and compartments on your desk, and you have the same problem. So the notion of having this folder is useful if there are not many documents in it and it's close by, you can access it. So that's the idea behind caches. Cache is basically a smaller storage medium compared to your primary storage that you can access faster than your primary storage. Now, what do you want to cache is usually the things that you need frequently. So things that you need frequently are good candidates to be cached, so that next time that you access them, you can access them faster. Now, why is this really important to use caches? The reason that using caches is is very important is the performance gap between your CPU and your DRAM. So if you look at this diagram, on the y-axis, I have the normalized performance growth. So how much performance improvement we've seen over the years, although I have to say this has plateaued. And so has this one. So both of them have plateaued. The gap between the two is a lot. So this means that your CPU can run on really high frequencies, let's say 2 gigahertz or 3 gigahertz, whereas your DRAM is going to run on really low frequencies. And as we discussed previously, for every instruction, you're going to go to your memory. And if your memory is slow, there is no reason for you to make your CPU faster, because you're going to just wait for your memory anyways. So what's the point of having fast CPUs? So this tells us that we cannot wait for DRAM. We cannot wait for DRAM accesses. We need to speed up our accesses to memory. Now, why does caching work? So initially, I told you the good candidates for caching are the candidates that you frequently use. Now, if you look at your access pattern, let's say I'm looking at let's say this N is a 32-bit system. So all the addresses from 0 to 2 to 32 minus 1 are demonstrated on the x-axis. And let's say on y-axis, I have the frequency or the probability of accessing certain address. Now, if I look at a certain time window, let's say I'm looking at, let's say 100 microsecond. During 100 microsecond, I'm looking at all the memory references that I did to memory. You usually see pictures like this. So with a bunch of peaks here and there, right? Now, what does this tell you? This tells you two things. First of all, if there is an address that I'm accessing a lot, the addresses next to this address, I'm going to go to them a lot as well. So this tells me a spatial locality, right? It means that, you know, if there is a certain address that I'm using a lot, the addresses next to it, I'm going to be using as well. So if there is this address that I'm using a lot here, the address next to it is going to be used a lot too. Now, if this time window is short enough, like 100 millisecond, or let's say, I don't know, 100 microsecond, then this also tells me temporal locality. It means that there are addresses that I'm accessing a lot. So temporal locality says if I access an address right now, there is a high chance that I will go to the same address in a short period of time. So if this delta is short, this graph is telling me that, yes, exactly, there are addresses that I'm going to visit frequently. That's temporal locality. And a spatial locality is the one that I mentioned. If I access address A, there's a chance that I'm going to access address A plus 1 and address A minus 1. So the addresses next to it are also going to be accessed. So given that this is the case, given that this figure shows a usual access pattern in our systems, it seems like we do have locality in our memory references. And if we have locality in memory references, caches make a lot of sense. Then we can cache these accesses in our caches, And then next time that I need them, instead of going to memory and spend so much time to access the memory, I can just go to my cache. It's that small folder on my desk, and I can get the data I want in a fast way. So some terminology before ending today's lecture. So when we're going to talk about cache in memory, we're going to talk about blocks. Now, a block is a single or multiple bytes in memory that are aligned. So usually blocks are 32 bytes, 64 bytes, and 128 bytes. So this is the unit of cache. When we ask what are we caching, we're usually not caching a single byte. We're usually caching a couple of a group of bytes that we're going to name as a block. Hitting in cache means finding the data that we are looking in cache. So if I say I hit in cache, it means that I went to my folder and I found the document I was looking for. If I say I miss in my cache, it means that I went to the folder and I couldn't find the document that I needed. So I need to now go and fetch that document from my boxes and my compartments. Now, hit rate is the number of times that I hit in the cache divided by all the accesses I did to the cache. So the number of hits plus the number of misses. So that's the total number of accesses. Now, this miss rate is basically 1 minus hit rate. So if my hit rate is 0.2, then my miss rate is 0.8. It means that an interpretation of this is like 20% of the time I hit in the cache, and 80% of the time I'm going to miss in the cache. So I'm going to go to the cache and I'm not going to find the data that I was looking for. Now, sorry, I think I missed something. Hit time, I didn't explain hit time. Hit time basically means the access time of the cache. So you go to the cache and you find your data. How long does this take? Now, miss time, you have to be careful. Miss time means from when you realize that you don't have your data in the cache until you go to memory and bring it back. So basically the time it takes you to satisfy a miss. So from when you realize that you don't have the data until the data is now ready. So that time is called miss time. Now, I can define average access time. For every access, how long does it take to get the data? Well, if you hit, you're going to hit 20% of the time with probability 0.2. You're going to hit, and you're going to pay hit time. Let's say 5 nanosecond in level 1 cache. With probability 0.8, you're going to miss. And if you miss, you've already paid the 5 nanosecond. You've already checked your cache and it wasn't there. And now you're going to go and bring it from memory. Let's say it's going to take 100 microsecond. So this is your miss time. Now, if you add this, this becomes your average access time. This is how much time on average it takes to fetch data from your memory subsystem. Okay, I'm going to stop here. So we'll continue from here on Thursday. Thank you for sticking around. Take care, be safe. We'll talk to you on Thursday. Bye.